Hello friends, welcome to this YouTube channel. Today we are going to solve a pair of numerical problems on three-phase induction motors. By solving these problems, we shall learn how to determine gross output power and gross efficiency of a three-phase induction motor for a particular value of slip using its per phase approximate equivalent circuit when values of circuit parameters are given. We have to estimate equivalent rotor current, stator power factor, power input to rotor, and gross efficiency at a slip of 5% for a three-phase induction motor having following per phase parameters referred to stator side. Stator impedance 1 plus j times 3 ohm, rotor standstill impedance 1 plus j times 2 ohm, and no load shunt impedance 10 plus j times 50 ohm. Given phase voltage 250 volts. Let us first write down the given data. Terminal voltage per phase ET equals to 250 volts. Stator impedance per phase Z1 equals to R1 plus JX1 equals to 1 plus J times 3 ohm, and standstill rotor impedance per phase referred to stator side Z2S dash equals to R2 dash plus JX2S dash equals to 1 plus J times 2 ohm. For any value of slip S, rotor impedance per phase referred to stator side Z2 dash equals to R2 dash by S plus J times X2S dash. Given slip S equals to 5%, that is equal to 0.05 per unit. Therefore, Z2 dash equals to 1 upon 0.05 plus J times 2 ohm. That gives us 20 plus J times 2 ohm. Let us now determine equivalent impedance per phase. ZEQ equals to Z1 plus Z2 dash. Using values we get 21 plus J times 5 ohm. This may be written in polar form as 21.587 ohm at an angle 13.3925 degree. Expression for rotor current per phase referred to stator side I2 dash equals to ET divided by ZEQ. Taking terminal voltage per phase ET as reference, we get I2 dash equals to 250 at an angle 0 degree divided by 21.587 at an angle 13.3925 degree. That is equal to 11.581 ampere at an angle minus 13.3925 degree. Given no load shunt impedance per phase Z0 equals to R0 plus JX0 equals to 10 plus J times 50 ohm. This may be written in polar form as 50.99 ohm at an angle 78.69 degree. Let us now calculate no load current per phase. I0 equals to ET divided by Z0. Using values we get 250 at an angle 0 degree divided by 50.99 at an angle 78.69 degree. That gives us 4.9 ampere at an angle minus 78.69 degree. This may be written in Cartesian form as 0.961 minus J times 4.805 ampere. We have determined rotor current per phase referred to stator side I2 dash equals to 11.581 ampere at an angle minus 13.3925 degree. This may be written in Cartesian form as 11.266 minus J times 2.6824 ampere. Applying Kirchhoff's current law at node P, we get stator current per phase I1 equals to I0 plus I2 dash. Using values, we get 12.227 minus J times 7.4874 ampere. This may be written in polar form as 14.3374 ampere at an angle minus 31.482 degree. For three-phase induction motor, expression for total power input to the rotor Pg equals to 3 times I2 dash square into R2 dash by S. Given per phase rotor resistance referred to the stator R2 dash equals to 1 ohm. Using values, we get Pg equals to 3 into 11.581 square into 1 upon 0.05, which is approximately equal to 8047 watts. Expression for total mechanical power developed Pm equals to 1 minus S times Pg. Using values, we get 1 minus 0.05 into 8047, which is approximately equal to 7645 watts. Since 1 bhp equals to 746 watts, Pm equals to 7645 divided by 746, which is approximately equal to 10.25 bhp. In polar form, we can write stator current per phase I1 equals to I1 at an angle minus phi 1 equals to 14.3374 ampere at an angle minus 31.482 degree. Let us now determine stator power factor. Cos phi 1 equals to cos of 31.482 degree, that is equal to 0.8528 lagging. For three-phase induction motor, expression for total power input Pin equals to 3 times Et into I1 cos phi 1. Using values, we get 3 into 250 into 14.3374 into 0.8528, which is approximately equal to 9170 watts. Let us now determine gross efficiency of the motor. Eta G equals to Pm divided by P in. We have computed total mechanical power developed Pm equals to 7645 watts. Therefore, eta G equals to 7645 divided by 9170, that is equal to 0.8337 per unit or 83.37%. A three-phase 415 volts 50 Hz star-connected induction motor has following per phase parameters referred to stator side. Stator impedance 0.2 plus J times 0.5 ohm and rotor standstill impedance 0.1 plus J times 0.5 ohm. The magnetizing reactance is 10 ohm per phase and resistance representing core losses is 50 ohm per phase. We have to determine stator current, stator power factor, gross power output and gross efficiency at a slip of 4%. Let us first write down the given data. Line-to-line terminal voltage VL equals to 415 volts. For star-connected induction motor, terminal voltage per phase ET equals to VL by root 3, that is equal to 415 divided by root 3, that gives us 239.6 volt. Given stator impedance per phase Z1 equals to R1 plus JX1 equals to 0.2 plus J times 0.5 ohm, and standstill rotor impedance per phase referred to stator side Z2S dash equals to R2 dash plus JX2S dash equals to 0.1 plus J times 0.5 ohm. For any value of slip S, rotor impedance per phase referred to stator side Z2 dash equals to R2 dash by S plus JX2S dash. Given slip S equals to 4%, that is equal to 0.04 per unit. Therefore, Z2 dash equals to 0.1 by 0.04 plus J times 0.5 ohm. That gives us 2.5 plus J times 0.5 ohm. Let us now determine equivalent impedance per phase referred to stator side. ZEQ equals to Z1 plus Z2 dash. Using values we get 2.7 plus J times 1 ohm. This may be written in polar form as 2.8792 ohm at an angle 20.323 degree. Expression for rotor current per phase referred to stator side I2 dash equals to ET divided by ZEQ. Taking terminal voltage per phase ET as reference, we get I2 dash equals to 239.6 at an angle 0 degree divided by 2.8792 at an angle 20.323 degree. That gives us 83.21756 ampere at an angle minus 20.323 degree. Let us now calculate working component of no load current per phase. IW equals to ET divided by RC. Given per phase resistance representing core losses, RC equals to 50 ohm. Therefore, IW equals to 239.6 divided by 50, that is equal to 4.792 ampere. Magnetizing component of no load current per phase Im equals to ET divided by Xm. Given per phase magnetizing reactance Xm equals to 10 ohm. Therefore, Im equals to 239.6 divided by 10, that is equal to 23.96 ampere. Expression for no load current per phase I0 equals to IW minus J times Im, that is equal to 4.792 minus J times 23.96 ampere. We have determined rotor current per phase referred to stator side I2 dash equals to 83.21756 ampere at an angle minus 20.323 degree. This may be written in Cartesian form as 78.037 minus J times 28.9 ampere. Applying Kirchhoff's current law at node P, we get stator current per phase I1 equals to I0 plus I2 dash. Using values we get 82.829 minus J times 52.86 ampere. This may be written in polar form as 98.26 ampere at an angle minus 32.5453 degree. Let us now determine stator core loss. PSI equals to 3 times ET square by RC or VL square by RC. Using values we get 415 square divided by 50, that is equal to 3444.5 watt. Now we shall calculate stator copper loss. PS copper equals to 3 times I1 square into R1. Given per phase stator resistance R1 equals to 0.2 ohm. We have computed stator current per phase I1 equals to 98.26 ampere. Therefore, PS copper equals to 3 into 98.26 square into 0.2, which is approximately equal to 5793 watts. Let us now determine total stator losses. PS equals to PSI plus PS copper. Using values we get 3444.5 plus 5793, that is equal to 9237.5 watt. For three-phase induction motor, expression for total air gap power Pg equals to 3 times I2 dash square into R2 dash by S. Given per phase rotor resistance referred to stator side, R2 dash equals to 0.1 ohm and slip S equals to 0.04 per unit. We have determined rotor current per phase referred to stator side I2 dash equals to 83.21756 ampere. Therefore, Pg equals to 3 into 83.21756 square into 0.1 by 0.04. That gives us 51,938.717 watt. Expression for total gross power output PM equals to 1 minus S times Pg. Using values we get 1 minus 0.04 into 51,938.717, which is approximately equal to 49,861 watts. Let us now determine total power input. Pin equals to Pg plus Ps. Using values we get 51,938.717 plus 9,237.5. That gives us 61,176.217 watt. In polar form, we can write stator current per phase I1 equals to I1 at an angle minus phi 1 equals to 98.26 ampere at an angle minus 32.5453 degree. For star connected induction motor, stator current per phase equals to stator line current. Let us now calculate stator power factor. Cos phi 1 equals to cos of 32.5453 degree, that is equal to 0.843 lagging. Now we shall determine gross efficiency of the motor. Eta G equals to Pm divided by Pin. We have obtained total gross power output. Pm equals to 49,861 watts and total power input Pin equals to 61,176.217 watt. Therefore, eta G equals to 49,861 divided by 61,176.217 176.217, that is equal to 0.815 per unit or 81.5%. So today we have solved a pair of numerical problems on three-phase induction motors. By solving these problems, we have learned how to determine gross output power and gross efficiency of a three-phase induction motor for a particular value of slip using its per phase approximate equivalent circuit when values of circuit parameters are given. Hope this lecture has been useful for you. If you have any suggestion or question, please drop it in the comment section below. If you have liked this video, give it a thumbs up and share it with your friends. Thank you.